Today we are going to have another category of DAC. So we learned 3 different architectures of ADCs as of now, and also one architecture of the DAC, which is charge distribution DAC. So charge distribution DAC naturally comes in the same category of DAC, in fact, architectures which are not high speed. But because we have already covered the high speed and low speed but higher resolution Nyquist rate, these are all Nyquist rate ADCs. So now we go with the high speed DAC. In fact, this DAC is not necessarily for high speed applications, but these days, in fact, not even these days, even from the past, recent past, it is used heavily for very high speed applications. So it's not a low power DAC when it is for high speed, just like flash ADC, but it is pretty fast. And it has some kind of similarities to flash, but in a other way around. Okay, so the reference is another magazine article of Razavi, the current steering DAC. Okay, so eventually charge distribution DAC, CDAC, was a kind of charge based or charge mode DAC. Everything was based on the charge stored on an element like capacitor. So this was eventually charge based or charge domain. Now we make it current domain. Eventually, instead of storing the charge, we directly use currents. And that's why, again, we are back to static power consumption. But we will have a very high speed. So therefore, this is eventually, I can call it a kind of current mode DAC. It's current mode DAC, but it is not known as current mode DAC. It's just that in the domain of current, or it is current-based DAC. Actually, it is called current steering specifically because current steering is a subset of current mode DAC. Current steering is a subset of current mode DAC. Okay, so as name shows, all we can do is that, first of all, we don't need any redistribution of the currents. We can just add currents and generate DAC. So it's a very simple concept, as simple as this. Let's say now naturally output also is a current, though you can easily convert it to voltage. But let's talk about current only. So eventually input is a code, binary codes, for example. And output is a current. And this is eventually, first of all, let's talk about current mode DAC. So this is not actually common mode DAC. This is current mode DAC. So here, we are not talking about common mode, this is current mode. So what is the overall explanation of a DAC? DAC eventually gives you the output in general. So if Y is the output, it's eventually a summation of the number of bits at the input multiply by their weighted, binary weighted value. So therefore, eventually with some LSB size. So therefore, it's eventually is 2 to the power, say, I multiply by LSB. Multiply by the same value of I, which is either logic 1 or logic 0. So therefore, it's just the value of, say, Bi, right? That is generic explanation. See, if you are talking about n-bit DAC, this is the generic. And why I write Y? Because I don't want to talk about current only. So it is eventually Y out. And these are discrete values. So these are quantized values. So DAC output is always quantized. So what we have is, in the case of current mode, the output actually becomes a current. Therefore, Y out becomes I out. Now, that means that eventually each one of these 2 to the power I LSV itself could be a current. Therefore, I can write it in the form of summation of currents. And this current, maybe I will call it J, because we have current Y as well. So this current eventually is 2 to the power J multiplied by some now unit current, just like unit capacitor we have. So here we have unit current, equivalent of LSB multiplied by Bj. So that's a mathematical description of a current mode DAC. Now question is how to implement it. So implementation also looks relatively straightforward because you can have current sources which are getting switched. For example, binary weighted currents which can be switched by the input bits. And then we are adding them. And how to add the current, it's enough to just short the branches. So we don't need to really have a separate module which adds the current. So eventually that means the simplest way, which is not used also, so this way. So the simplest way is you just put these branches, which are binary weighted currents now. So therefore, for example, here 0. Yes, correct. Thank you. So yeah, so let me show also current direction downwards because I showed I out also downwards. So you have these current sources. And the weight of each current source in general is proportional to the position it has. For example, if this is LSB, so therefore this will be I unit. And if this is MSB, so this will be 2 to the power n minus 1 I unit. Because if I disconnect all of them, then current will be 0. So I don't need to have anything specific for 0. All I need to do is to add some switches here. So therefore, I add switches. And what controls these switches? For example, for the first switch, control is with B0. For the last switch, it is with Bn minus 1. So that means if Bj in general is 1, the corresponding binary weighted current will be on. So this is simple, very simple, directly also binary weighted, and directly will give us this expression. So we have a DAC, output is current, we can convert it to voltage. This configuration is not used. So we have from 0, B0 to Bn minus 1. Okay, okay, sorry. That was your point. Yes, yes. Actually, we have both of them in this, that's why, yeah, this is correct. This is binary. Now, this is eventually is used. In fact, in high-speed circuits, we usually try to avoid this configuration. This configuration has some problem. In general, for high-speed applications, low speed is okay. So let's say this is a current generator. So therefore, I don't show it even with the ideal current source. It's a current generator. And here you have a current I, and this is connected to some load, and say this is VDD. And this is load. See why for high-speed applications this is a problem. The problem is that at the end of the day, this is a circuit which generates current. When you open the switch, you are enforcing the current to go to zero. That means the whole block which is generating a current, whether it is a single transistor or multiple transistors, eventually will go to completely in off mode. Now, when you close the switch, you have to wait for this circuit to have its own settling time. And you need to wait enough to make sure that current settles in this value. Otherwise, you will have error. So this naturally slows down the operation, because you cannot just say that, okay, I just give a short time to it. You cannot give. You need to wait till current settles well within the very small fraction of LSP to the final value. This means that this has to be pretty fast if the speed is high, and that's the problem. There are other problems also, I tell you. So this is the first problem. Therefore, the first problem is that T settling of I. So this is the first problem. What is the second problem? For high-speed applications, see, when you have a connection to the ground, this is not actually the real ground. You have a package which gives you the VSS. You have routing. Specifically, now we'll see, if you want to increase number of bits, you will have a lot of routing, metal routing on the chip. So actual model is this for VSS, because this goes to outside volt. You have to take it out from die. Even if you go with the today's, in fact, today's advanced packaging techniques like chiplets allow to reduce these effects, but still they are there. Because at the same time, those technologies are for really extremely high speed application. And when we say high speed, that means that tens of or hundreds of gigabit per second. At least tens of gigabit per second, going above 50 gigabit per second. So this is really an issue. Why it is an issue? Because you want to turn on this current on and off very fast. So you will have, first of all, you will have anyway, let's call this R parasitic. I just call it R parasitic. And this is L parasitic. L parasitic comes usually because of packaging. Now imagine that you are giving a current which goes on and off and passes through this RL circuit. Because of the value of the current, which could be high because of the speed operation, then this will create a delta V. Or if you are operating at low supply voltage and the amount of current which flows and the load multiplied by the load is not very high. So therefore you have limitation. You cannot spend a part of this headroom from VSS to VDD, which is actually zero here, to drop across this R parasitic. Therefore, routing of the ground line has to be done very carefully. Another problem with this equivalent inductance of this interconnects as well as connection to outside volt. That's why usually there is a capacitor also here, which is called decoupling capacitor to reduce the effect of inductor. So you have, and this we actually put on chip. It's a huge capacitor, but it's okay. You have an empty space on the chip. So therefore, this is not actually this ground. Okay, so it is something. So eventually, this is outside. See, it's like this node is outside. This node is inside the chip. And this inductor is sitting in between. So this is actually the ground which is outside, right? So you have a ground which is inside. So let's call this internal VSS. And this is external VSS. Right? Okay, so I have to correct also this capacitor is outside. So this is only the pin capacitance. It's not a very high compared to actual capacitance. We usually keep over here. So because this is your internal VSS, now because of routing, you have a local VSS as well. All you can do is that you can connect it to this node. Also, there is also a pad on the chip sitting somewhere, which could be more than one, say 2 of them. And these are VSS values. We make more than one when the current levels are very high. So here, actually, this is the routing which finally will come over here, right, on the chip. These are all on the chip. Only this side is outside. So therefore, we try always also, as much as possible, to create a kind of capacitance between all these internal VSS nodes. See, this is an internal VSS grid, and this is another local VSS. And then we try also to add capacitors here, because there is a resistor here, a large capacitor. So that all these nodes are effectively trying to get into the, specifically if there is a very high bouncing on the line. And here actually this bouncing is created because of this inductor. That's why this is one of the reasons also that really we don't want to have a high current to go on and off continuously because of the parasitic effects. In fact, here also you have this inductor. See, this inductor effect, because of the connection between the external volt, this is like, okay, sorry, this is not here, this is the other side. It's here. And this is connected to the, again, external VSS on the board, for example. So it's actually the connection is that way. Even here also there is a pad. I mean, if I want to be very, very precise, let me draw that pad as well. So you see effectively here there is another pad, and then one inductor, and then connected to, say, external VSS. So this is that connection. One advantage, of course, is because all these paths are shorted, you are making parallel inductors. So it will reduce, in fact, the effect of these inductors. That is another advantage. But in general, we don't want to have something called ground bonds. Ground bonds is one of the problems in low voltage, high speed operation. Low voltage, high speed operation. Because you think ground is very clean, which is not always true, even on the chip. So therefore, more switching of the currents, you have more problem. In fact, large digital chips, a full-fledged, say, very high-speed processor, any kind of, any computational core will have this kind of bouncing on the ground. That's why this is something. In fact, here also you have. In fact, every connection to the outside world, you may have some inductive effects. And internally even. That's why these lines need to be really, it's okay to have very high capacitance, but they are not supposed to have a very high inductance. So right now I'm just showing an ideal line, but actually here also, for example, you may have some series resistance of these lines. So that's why all this RL network creates ground bounds. And that's why we try to avoid this. So anyway, we are switching them at high speed. That means dynamic power is already anyhow high. So therefore, there is no point to be worried about static power. Therefore, the better technique which comes to rescue is that to use differential architectures. Not only we get better swing, but also we would be to with a similar current, but we would be able to get also the kind of constant current drawn from the supply. Now let's have an idea of just a similar configuration in a differential manner. Let's show it with one of the current sources only. So this is the simplest case. Let's say now we show it in the transistor level. So suppose this is a V bias. This is coming from current mirror. Okay, let's say right now we have just a common source configuration, current mirror. We have 3 CM, current mirror, current mode, common mode, current mirror. Say this is, say, tail current source. Now we have 2 transistors. Let's say, for example, this is M1J, because every current source has these transistors, and this is M2J. So this is a differential configuration. This is a current source, and we take the current. And because we want also to use these currents, let me connect some resistors over here. I don't want to keep it open and tell you, okay, we take the current only. Let's say we are flowing the current in these resistors R1 and R2, where R2 is equal to R1. So it's a simple differential amplifier with resistive load that you are quite familiar with it. And now let's give the digital inputs here. That means this will be BJ, say, and this will be BJ bar. So this is a simple DAC. And this is called actually current steering DAC, because current is steered between these 2 transistors, depending on the BJ. But the current which is flowing into this ground or flowing or taken from supply, it is fixed, it is I tail. So you have a fixed current. You get rid of the bouncing issues which are created. Still you have the IR drop. IR drop problem is a static problem, is not solved, but at least problem due to parasitic inductance is solved. So therefore, what eventually happens is that now we have a static current flowing. And that static current anyway is the same current, and this is high speed specifically, switching continuously. So therefore, it's not like that you really get benefits if you don't have a static current, because we mentioned here, the problem with this case when you want to turn off the static currents is that you cannot use it for high-speed applications. Fine, so this differential circuit will give us the advantage. Of course, easily you can see if this is, say, for example, just we call it I out plus, and those which are connected to the inverter of the bits, we call it I out minus. So therefore, if you want to take the current rather than voltage rather than current, you can take this differential output. What is the application of this current mode DACs? They have a lot of applications. A very simple application, not simple, okay. A very common application is the applications which are used in wireline communication. For example, data centers, driving cables which are connecting different racks, right? So for this data communication over lines in, say, data centers, there you need a very fast, data, very high data rate, fast data transmission over lines to bring it from one block to another block on the whole system. This is not on the chip. So therefore, effectively, you need to drive a transmission line, say, or a cable. right? Say I show right now one only. But say this is, for example, transmitter and this is receiver. CMOS will fail. So CMOS logic cannot be used for this application. That's why other logic families where this current mode logic, current mode signaling is called as well, practically is used. And this is actually in the form of a DAC. So therefore, what they do is that you don't need to connect resistors for all these connections. It's actually only one resistor. And if this is a 50 ohm line, which is the standard, it's enough to add 150 ohm here. And if it is differential, 2. So it's eventually 2 lines, 2 eventually properly shielded lines. So it arrives on the board or on the cable, and therefore you have 2 outputs. So you add all these currents. In fact, if you want to show it that way, so eventually you have all these I out plus and I out minus values which are getting added. Say this is the differential circuit 1. Say let's say we are showing only for 2 cases. So these 2 are added and the other 2 also are added. So this is say I out minus 0. This one is I out plus 1. The other one, this side is I out plus 1. I don't write the other 2. You know that this is I out plus 1, I out minus 1, and this is I out plus 0. And then this can be directly given to the line, and each one of them will see a 50 ohm. So therefore, and the supply is on the other side. This is one way. There are other ways as well, on side at the receiver side. Or it can be connected to a resistor at the local transmitter and then connected to the load, which is over here. So there are ways, but usually this itself is a part of transmission line. So we don't need a separate resistor over here. We can directly remove them, connect them to the transmission line and derive the DC current through the line. This is one option. So therefore, all we need is a set of these differential pairs, 2 resistors, which could be at the receiver side even. Therefore, transmitter needs only that part and the connections. And of course, when we increase the number of bits, let's say for example, if we move to the say 10 bits, then you will need eventually 10 binary weighted cells. And that is where again the same problems we had before with respect to SOR ADC here also will show up, because now these binary weighted currents all should be a binary properly matched version, weighted coefficient for IU, right? And all of them should be satisfying this binary weighting. So that we will come later. So, but at least now we have some idea about how to make it. Any question till now? Clear? So the purpose, the motivation is clear. This load usually is not a very high load. As I told you, it could be as simple as 50 ohm. This is high speed, and therefore when you move to high speed, all resistors become small, like RF domain. Everything is 50 ohm, 75 ohm, 100 ohm domain. So therefore, therefore here we understand the whole information that we get is the swing. Eventually this is V out D. This differential output is actually output of the DAC. This differential output now will have, how much would be actually the full scale range of this V out D? It will be eventually the max value multiplied by minus mean value. So max value eventually is when, so let's say V out plus max, which is same, will happen on the other side for the negative. So this will be, let's say VDD, right? When no current flows, current 0. Say all bits are 0. Therefore, the current flows through resistor R1 is 0. R1 is common, connected to all cells. But the current drawn from R2 will be maximum. Similarly, other way around. If the Bj is 1 for all, then the current I out plus is maximum and the V out plus mean will happen at that case. So that will be eventually VDD minus I full scale. I mean, if I go with differential, it is upon 2. If it is single-ended, it is upon 1. This I full scale eventually is the summation of all currents, tail currents, binary weighted flow. So similarly for V out minus, now I will write in mean. So it will be same thing, VDD minus I full scale D upon 2 and V out minus max is VDD. VDD doesn't play any role in differential output, it's just a supply level. So therefore, V out plus or V out D eventually, max will happen when we have the plus output, my single-ended plus side, VDD, and this side. So it will be multiplied by R. Multiply by R. So will be, max will be I full scale D upon 2 multiplied by R minus minus, so which will be plus I full scale D upon 2 multiplied by R. So eventually it will give you I full scale differential multiplied by R. So this is the swing. And as you can see, this is eventually our full scale differential. Yeah, V out plus max minus V out minus. This is actually V full scale. Now, because the other way around also will give you only the opposite. V out D max. Okay, so now let me write the V out D mean as well. V out D mean will be VDD minus, yeah, here, this one minus VDD. So that means when V out, no, that's actually correct. This is actually peak to peak. That's already I have written. It's not max, this is actually peak to peak. Yeah, this is not required. This already implicitly I calculated, like for example, V out plus max and then V out minus mean. These two will happen together. So we'll give you maximum positive and this is maximum negative difference. Yeah. So this will eventually will be I full scale D multiplied by R. So now you see, or if R is 50 ohm, suppose. So if IV full scale, how much? Say for example, 10 milliampere. So if it is 10 milliampere, suppose, equivalent eventually, 10 milliampere. So it will give you 0.5 volt. So that is what you have. That means if we have a supply of 1 volt, we have only 500 millivolt for the rest of the circuit. See, I just called it I full scale D upon 2 because in differential always you get the double swing. Otherwise, but that is actually the same I tail, corresponding current which flows.
So full ideal will be flowing through.
Almost, yes. We assume that the difference of these two is in such a way that most of the current actually flows through M1J. No such current flows through M2J. M2J is going to subthreshold. Yes.
So ideal scale is just like a representation. It should be.
If I want to write it, I have to write it in the form of I-tail and summations. That's why that right away I wrote it, because I'm writing the maximum and I call it I full scale. This is actually full scale single-ended. Full scale single-ended is binary weighted sum of all these currents, single-ended.
But some of all those currents should be
Single-ended.
Some of all those currents single-ended is
Be full scale. Single-ended be full scale. Yes, single-ended be full scale. Because you see that if I look at the V full scale, I have this value as the swing. If I look at the differential, I will have double of that. That's why I define this as V full scale. I can call it V full scale. See, this is actually this whole thing. Okay, I can write it on the top. I full scale, single-ended now, right, is actually summation of all currents with a weight of 1. That is 2 to the power I multiply by I unit. J is changing from 0 to n minus 1. Right? So this is actually single-ended. But differential will give us the. When you have V out plus max, you will have V out minus mean together. I full scale upon 2. This is for maximum. For minimum value, you have the other way around. And difference of them will give you peak to peak. And that's why always it becomes double. Even full scale range becomes double. So this is eventually, see, these two happen together. And these two happen together. So we may go all the way from here to here. So it becomes peak to peak. Okay? Fine. Yeah, so these are the kind of scale of current, like 10 milliampere. We are not now talking about, don't talk about, we are not even talking about 1 milliampere. It's more than that. By the way, there is one advantage if it is possible. There are some ICs when the back side of the package is actually directly grounded. And if there is connection from the top metal sides to that, then you can actually get directly connection to the VSS of the board through that connection. And that's why these issues also will reduce further. On-site, this is on the chip, this is outside the chip. And this is what is sitting between them. No, ideally you think there is one ground, right? Because you are shorting them, these are metal. Yes, on the board, say, for example. So say this is a VSS pad, right? You have, say, a VSS pad which goes to the pin. Pin is here. So therefore, this connection is on the board, say PCB. This is PCB. And here is the interface between chip and PCB, which is the package. So therefore, whatever you have above yellow color, this is on the chip. Even these I/O pads are windows which is on the chip. They are actually stack of metals. They connect some kind of metallic connection here to bring it to the outside world. There are different now techniques for that. So this is that interface, that method of packaging. It connects the outside. In fact, this is a pin, what we call it pin on the IC package. Pin of the IC package is not directly the pad. Technologies have that. There are technologies expensive. If that is the case, that's the best case. Even that contact still may have some inductive effect when we move to high speed. Therefore, we put this parasitic inductor here. And as I told you, even on the chip, these interconnects are not pure interconnects. They have actually some minor inductor. But this inductor effect usually is more. So therefore, yellow color upwards is on the chip. This pin is outside on the PCB. And they are connected using some way of technology which connects them. And therefore, these I/O pads will give you the internal VSS. And this is what external VSS. And we think that these two are same, but not necessarily. In fact, if you look at the large digital chips, and if you look at their VSS as a function of time, so let's say VSS should be 0, right? So ideally it should be 0. Now what will happen is that even by simulation, you would assume that this is a real VSS, just make it 0. This VSS compared to that real VSS will show you this kind of behavior. And this can reach to, say, sometimes plus minus 100 millivolt, plus minus 50 millivolt. So already it's actually consuming some of the headroom. This is very common. In fact, by simulation, it easily shows up by just putting some typical values of inductor. These typical values change, say, from a few nanohenry down to 1 nanohenry and below. So a couple of nanohenry is common. But when you make them parallel also, it is helpful to reduce. Okay, these tail currents are binary weighted, ideally. So therefore, for the bit 0, it is I unit. For, I think I wrote here, somewhere I wrote. For, anyway, for the, yeah, here, it's here. For the, no. If all of them are connected to the I out plus, you have summation of all of them. That's why it is full scale. Upon 2. Only 1 bit. 1 bit deck will be only IU and 0. So it is IU and minus IU eventually. So it will give you 2 IU. Because we are looking differential. See, let's say look at the difference of currents. Forget about even resistor. I out plus is, say, IU. I out minus is 0. So you will get IU differential. The other way around, IU plus let me write it for 1 bit. So suppose B0 equal to 0. So I out plus is equal to 0. I out minus equal to IU. And B0 equal to 1. So I out plus is equal to IU and I out minus is equal to 0, right? Now here I out D is minus IU and here I out D is plus IU. So difference is 2 IU. That's why full scale doubles. So single-ended full scale, say for 1 bit is IU, for 2 bits is 2 IU. That's why I wrote it V full scale D upon 2, which is actually single-ended. Now, we didn't have an opportunity in the SAR ADC to get rid of this problem of matching. Of course, there are calibration techniques which actually adjust the values in the software and sometimes even on the chip, this mismatch issues. Layout also, of course, is very important. We had some discussion about layout of capacitors, and in reference paper from Leo also you have seen the arrangement of capacitors on the layout. But here there is an opportunity which didn't exist over there, and that comes because these are all current sources which are eventually can be made parallel. So if I have 2 to the power j IU, that is eventually summation of, okay, yeah, k from 1 to 2 to power j, eventually IU, right? something like that. That means that you can actually add unit currents. Only the number of unit currents you add are really high. What is the problem? Problem that we had in SOR-ADC that we have here also in binary weighting is that, suppose, let's go with 3 bits. If I have, say, 0, 1, 1 and 1, 0, 0, do you remember this was one of the problems? Because here you have eventually summation of, say, IU, and I write it random variable 1, then you have, say, 2 times of IU2. Assuming even IU2 and IU1, IU2, IU2 are same. There is a mismatch between them as well. But for now, just for simplicity, right? The same way we did there. This is eventually for IU3, right? So if you jump from, say, this is only 2 consecutive bits. Their difference is only 1 LSB. But their analog values can have a difference of more than 1 LSB easily. Because let's say if these currents have, say, value of IU minus delta and this has IU plus delta. In fact, as soon as you switch from a network to another network, when there is no common element between networks, chances of getting a huge mismatch or variation is high. Now, this problem can be solved if you go back to flash ADC. In fact, flash ADC and current steering that from some aspects are dual of each other in the ADC and DAC domain, and both of them are high speed. And both of them are power hungry. This is the physics behind any analog circuit. So, what if we use thermometer code? Do you remember flash ADC was actually generating thermometer code? What if, and we were converting thermometer to binary. So let's convert binary to thermometer. What was the advantage of thermometer? One comparator only output was changing when the input was changing, analog input by 1 LSB. So here also we say that even if we have the code changing by 1 LSB, we have this issue. We have the same issue in SOR-ADC. But there we didn't have an opportunity to correct it. Here everything is parallel practically. Just like flash ADC. So if we convert binary to thermometer, only catch here is that we should have this decoder. Binary to thermometer code. Okay, so I don't have a space, I just write T code. T code means thermometer code. Now you have a thermometer code at the input. So number of bits, of course, will increase for thermometer code. And therefore, routing will be much more difficult, right? If you have, for example, a 3 bits at the input or 3 lines at the output, you will have practically all these lines. How many lines? How many lines? 7 lines. Actually, there are 8 lines because we have to give the input to all of them. Yes, I agree with you. If all are 0 is same. Fine, 7 lines. So eventually 3 lines becomes 7 lines. Naturally, if you increase it to say 6 bits, it becomes 63 lines. So number of lines. This is of course one of the issues because these are all high speed as well. But advantage is that at a time only one of them will switch, right? From 0 to 1, say, or from 1 to 0. That means now you have many lines, which looks like a drawback, but then the switching which is happening is not this way. Now say for 3 bits, say for example, now you have thermometer code. So therefore 0 is this, 1 is this, so 7, 3 plus 3, sorry. Three. So this is 1. And then this is 2. sorry, 2 is 2 ones, and then 3 is 3 ones, and so on. So therefore, when you move between two consecutive codes, only one bit will change. So this problem now will be solved. See, name for this is something already we know, but in the context of DAC, they call it segmentation. I am not sure about historical reason, but this is called segmentation. This is eventually converting binary to thermometer and switching one. Eventually, we are now moving away from binary weighting. It is implicit, of course. Still, we have the same number of I unit elements. We have 2 to the power n minus 1 IU elements. But in the case of binary weighted, each one of the current sources is eventually scaled, right? For example, if this is IU for the LSB, for the next one should be 2 LSB, and the next one should be 4. That means W by L of the next L transistor should be double, and next one should be 4 times, and next one 8 times. Here all of them carrying same current, but number now has become 2 to the power n minus 1. So eventually, to have the comparison of the two cases, so without segmentation, it will be, say, IU. So I'll go from MSB to LSB. 2 to the power n minus 1 IU. These are the tail current sources. 2 to the power n minus 2 IU. Then we will have, say, 4 IU, then 2 IU, and 1 IU. 0 naturally will be, all of them are disconnected, it will give us 0. Now with segmentation, so eventually you have IUs, all are IUs. So eventually you have 2 to the power n minus 1 IUs. All are, in fact, all of them are IU. So that means you have IU, comma IU, comma IU. How many of them? 2 to the power n parallel IU elements. It's eventually 2 to the power n minus 1. Number is very high, but they are all parallel, not parallel, okay, single IU current sources. Therefore, instead of having tail current sources to be of these ratios, of these weights, and therefore changing the aspect ratio of tail, now all tail current sources also will have same aspect ratio. All will be having, say, W upon L, and same. And therefore, now number, of course, will change. For example, for 8 bits, we will have 255 current sources. Here we will have, for 8 bits, we will have 7 current sources. But the 7th one actually is having a very high aspect ratio of tail. This transistor also need to be accordingly scaled. So now that will go away, but now we have a very long kind of layout. Again, is very important. And as we discussed at the beginning, too many interconnects also at the output, at the ground level, at the VDD level. We have to take care of the series resistance. Because imagine that ground has to go all the way from left to right. How much would be the effective resistance of such a long line? So that's why that routing is very important. So eventually, this is extremely routing should be taken care of. And another advantage also is that because there is only one bit at a time, cross-coupling, crosstalk effects will reduce at such high speed. because only one bit is changing at a time. In the previous scheme, many bits were changing at a time. Therefore, here even routing will be more problem because you need to make sure that there are not cross talks between the lines, between the bits. See, by the way, we didn't talk about the Bj and Bj bar. We assume that they are logic high and logic low in CMOS. See, one of the problems is that in CMOS again, though at high speed, logic high will not reach VDD, will be less than VDD. But let's say it is close to VDD or it is above ground, 0, but it is close to VSS. See, one of the problems is that if you want to keep these transistors in saturation, this Bj cannot be close to VDD, then the drop here is very limited. That's why usually it is preferred to have even inputs also, not really CMOS level, which is happening practically due to the high speed logic. But if not, then there should be a kind of reduction in the VDD or high logic level corresponding to BJ. Low still should be okay, but high definitely should reduce. This is one of the problems. And we prefer these transistors to be in saturation because it will not have impact on the current because output impedance will be high. See, if you drive transistors into ohmic region, effective output impedance you see from drain of this transistor will reduce. So therefore, I unit itself may change. So that's why we prefer not to put. Therefore, this is also another point about the swing on or logic high. In fact, logic high for B0, for B eventually, J and Bj bar. This is one of the things limiting the swing. Limiting swing at the output, eventually across the final. These are usually called termination transistors also because this DAC is exactly sitting next to the I/O. Output goes to the cable or to the trace on the board. So that's why these are usually called termination resistors. Even these resistors could be on the board. Even at the receiver, they could be on the board rather than to be on the chip. Advantage of putting them on the chip is because you can make a precise 50 ohm. If you put them on the chip, they will change with the process variations. That's one of the problems. That's why they can keep it on the board because these are all high-speed board design. Okay, any question till now? So at least we learned. By the way, because this segmentation also results in too many units which have to be connected to each other, if is not required, is okay to actually only apply to bits towards LSP. Bits towards MSP will not create such a problem because even there the variation will not be very high. See, this is almost middle of the code. Right? This is exactly middle of the range. So if you move towards LSP, for example, only LSP is swinging, or the last 2 bits. Therefore, there is a combination as well. For example, the first 2-3 bits are binary weighted, the rest are segmented. That's a combination also is possible. Then we can have some discussion about the INL, DNL, at least with respect to operation. So design will come after that because we need to look at non-idealities and then we'll talk about the design of this current steering deck, how to design them. Eventually, for the design, we have tail currents, which are usually mirror transistors. We have sizing of the differential pair. Resistor is more often given to us because it's a system level decision. We don't have much freedom to choose R. And VDD also is given. So therefore, we will keep the design for later, but now we can look at the mismatch and process variations. See, high speed also is like high frequency. What's the difference between high speed and high frequency? Any difference? In the technical domain, there is a difference. That's why high speed and high frequency are used as two separate domains. Applications also are different. See, in high frequency, as name shows, frequency is high, but it could be a single frequency. Therefore, you have a narrow bandwidth, not necessarily a wide bandwidth. So therefore, your focus is on the frequencies only, but these frequencies could be in a very narrow band. In high speed, you deal with signals in time domain, which can have many frequency components, but they have to be fast enough. See, one of the examples that high frequency always doesn't mean high speed is the slowing in op-amps. A very wide band op-amp is not necessarily fast, because there are large signal effects which makes it slow. But frequency domain analysis and unity gain bandwidth are not in large signal. So therefore, though it is very wide band, but it will not work well if it has to have a very short transition, because short transition may be due to the regions that the system is not operating in the region that is designed for. That's why we need to look at those aspects. Here also, we are not really looking at the frequency of input. In fact, in digital systems, digital circuits or logic signals, it's very difficult to find even the bandwidth, because you deal with, say, sharp edges. So even a clock is not a single frequency, right? If you draw a spectrum of a clock, it's not a single frequency, which is the frequency of clock. Those sharp transitions, unless if they are a very small fraction of the frequency, then it is not a big deal. So that's why you cannot transmit, because one of the questions always is this: okay, can we just remove this physical, in fact, metallic channel and use air? Why we cannot connect cores, say multi-cores computational cores, using wireless links? Because bandwidth is too high. Wireless communication is based on a limited bandwidth, very narrow compared to carrier frequency. That's why other channels, like optical channels, are used. Like, for example, fiber optics are used for high-speed data. That is exactly the way right now technology works. That's better than what is available in semiconductor domain, because it's a metal-oriented, copper, gold-oriented interconnects. But there is a optical. Optical is better, but then you need to convert them to optical. To convert them to optical, again, same thing. See, if you want to convert electrical to optical, you need still to use this circuit, because this has to drive the optical interface. For example, drive the current to light conversion, for example, using say, a light generator. I don't call it LED because it's not necessarily LED, but it's eventually you want to generate a specific kind of well-defined optical domain signal. So you need to use this to give it to that transducer, which converts electrical to optical. So therefore, this has a lot of applications. In fact, optical interfaces also need this kind of circuit. Okay, so now we look at the non-idealities. So of course, one of the non-idealities we already looked at, and then we said that by segmentation or partial segmentation, it can be reduced. And that eventually means INL and DNL will improve. Okay, so therefore I don't need to draw INL, DNL for this case that I gave example, because already you are familiar with. So we talk about one more effect, which is very important. So eventually, therefore, let me just write here. So therefore, with segmentation, DNL improves. Yeah. Because problem with the binary weighted is actually DNL, it's some codes, and that improves. The rest will remain same compared to unity gain sizing. So one of the other problems is that anyway we are using transistors. Now let me draw the small signal model. Now let's say we have even unit current, it means that unit current source. So if analyzing in small signal domain is easier. So this is, for example, now this is thermometer code. I cannot here write BJN. So let's say, for example, just some input signal. Now let's forget about this. So V in plus V in minus. Yeah, we call it this way. And these two were resistors. And we know that many of these parallel transistors are connected, right? So this is only one of them. So similarly, we have more. Effectively, if I want to show, I can actually show this way, like how many transistors are in parallel. So here, eventually this transistor is representative of n parallel transistors. Parallel transistors, right? How many will be left here? So if m transistors are here, this side we will have 2 to the power n minus 1 minus m parallel transistors. If we go with a full segmented ADC, right? So analysis actually similar for any kind of even hybrid case, but let's say for this case, segmented. In fact, in fully segmented, because we have the maximum number of transistors, we talk about that. But at the same time, in the binary weighted, the aspect ratio will increase and the current will increase. So therefore, they are equal from this analysis point of view, fully segmented architecture. Right? So we have 2 to the power n minus 1, and all of them are eventually only, we have every unit only has one current, I unit. See, if you look at this circuit closely, if you have n parallel transistors and output resistance of each transistor is RO, effectively you have RO divided by M as an equivalent resistance. And this side it is R. Right? And say this is V out plus. See, I call V out plus exactly same as V in plus, not because of polarity, but just because it is at the same location. Same transistor, same side. So now you see that, so there is a loading effect. So loading effect of these parallel branches, if output resistance was infinite, no issue. But now because of that, as we increase number of bits in general, no matter even what is the architecture, as long as we increase the number of bits, we will have the problem of loading. Now what is the effect of this loading? So we can see that as we increase M, one side, Say, for example, here m is on the left side. So m on the left side, we will have more and more issues as m increases with the nonlinearity. Why? Because it is equivalent by saying that if m is equal to, say, 1, we have, say, equivalent with decimal 1. So effective resistances are O parallel to R. If m is equal to 2, effective resistances are O upon 2 parallel to R. This is nonlinearity, right? That is equivalent by saying that now LSB is changing. Because LSB is defined I unit multiplied by R, single-ended. VDD is not playing a role. So I unit is not anymore I unit. So eventually this will be multiplied by I unit. And for the m equal to 2 will be this. And now if we increase it to some m equal to, say, k, this will be Ro upon k parallel to R multiplied by I. Now what would be effectively the, first I will draw the single-ended, then I go with differential. Say, suppose I want to draw the characteristics of DAC. So here is code, and here is the V out plus. I just show the single-ended right now. This is only small signal. So this is, and codes are in decimal. And this is also V out plus divided by IU to make it only a part. And this is the code in decimal value. Then suppose this is 1, this is 2. Now I move to higher values. Just to see what happens. 4, 5. We just continue, just to see how it is. So here there is one value, which is 0. That is well defined. Now for 1, say I am somewhere here. I have to go higher as well here. So at 1, so I'm not including, and this is only large signal. And actually this is also minus. Okay, so it is okay. These are all just minus. Here I will put absolute value of a small signal. So this will be first one. Say it's here. RO parallel to R. Next one now will be less, right? So therefore, if I'm supposed to have it, I mean, 1 bit may not be a significant difference, but just to show you. So next value was supposed to be here, next value here, right? And then you will have a straight line. This is the characteristics of ideal DAC. Now here, if I just continue with the, okay, I have to reduce this, otherwise I will not be able to cover all. So let me reduce. Okay, go here, 1 is here, 2. How many I want? Say 10. Let me see how I can do it. This is, say, somewhere here, then here, and here. 1, 2, 3, 4, 5, 6, 7, 8. That's okay. We will go till 8. So these are the actual points. Right? And just continue almost like a straight line. Now, because of this effect, effectively, as we move towards higher codes, because more number of transistors will be series with each other, this value will start reducing. I show it, say, yellow color, just to give some idea about it. Suppose here, it will be closer to this will be very close, and it's almost matching. So that means that if this is the ideal case, I hope my ideal case will be ideal. Wow, so nice. Okay. Move one. This is almost like a line. Now the yellow color actually are the real values. So suppose now this has moved down. So we are somewhere here. This also has moved one less. Then here, then say here and here. So that means that effectively you will see this kind of effect. That means it's gradually reduced. That means that if I want to show it really how it will be, if this is the ideal characteristics, real characteristics will be becoming something like this. It's eventually bending. The reason is because size of LSB is reducing as we increase the code value. No, not necessarily. That is exactly the point. This is okay for low number of bits. What you say is manageable well, because this error is one of n number of reasons for distortion and eventually INL DNL error. This is actually nicely shows the INL, right? It shows eventually how this characteristics is switching points are changing. So it's a representation of INL or distortion in characteristics, so that instead of line we have a kind of curve which is also bending. Here, if you want to choose R to be much less than RO upon K, so this is the question. Let's go with an example. No, suppose if you have 10 bits, this is 1024. If you have 8, so if your good currents are in the range of hundreds of microampere. Keep in mind, this is high speed. If you go with a very low current, there is no issue. But even that also, see, there are three things which are trading with each other, and they have trade-off. See, let's see these three things that makes this situation not so straightforward to deal with. For low number of bits, 3 bits, 4 bits, manageable. As we increase the number of bits, we want to have enough swing. Fine. Therefore, for us, value of IU matters actually, or IU matter. So this is the unit, eventually LSB size. We cannot make it too small. If I want to make it small, we have to reduce IU or we have to reduce R. Let's say R also is given to us 50 ohm. We don't have any choice. So therefore, R is 50 ohm. Usually I told you like this is not so straightforward to choose, but even if you choose, you will be around this value ranges, hundreds of ohm, not really very high. So now if IU is, now this is something which will determine for you the swing. Why this swing matters? Because this swing goes to the line, and because of losses on the line, it will reduce. At the receiver, there should be a reasonable window so that it can be detected. So therefore, this swing cannot be too low. Also, other effects, like for example, switching noise, internal noise will start showing up. So this is one thing. So we have a question about swing. The second thing is that number of bits n. So if number of bits are high, so we have effectively division by this value k, right, which is 2 to the power n minus 1. Let's say, for example, m is 2 to the power n minus 1. That means that this side is divided. So therefore, what we want is that r o divided by, say, let's say n is equal to how much? 10, yeah, because it's round. So it is 1023, right? This should be much more than r. That's the only way to. Eventually, if we make this is ideal case, because now effectively we say that INL due to this effect is negligible. So therefore, we are going to the extreme to make it negligible. That means RO should be more than, much more than in fact, 102.23 multiplied by R. So R is already, say, 50 ohm. So if this was 1000, this becomes 50K. So let's say RO should be well above 50K. Well above. That means that at least make it, say, 5-6 times more. So it will end up around something around mega ohm, right? Say 10 times more. No, actually it will be around 500 kilo ohm. Fine, 500 kilo ohm. Now, going back to RO. RO has an inverse relation with current, right, in any transistor. And to make it high, you need to make these transistors not to be short channel. So now you make these transistors long channel. So therefore, now what will happen is, now parasitics will start showing up here. This is not a resistor now anymore. So it will be also parasitic capacitors. In addition to the capacitors, it is eventually will have from the same thing, IOs. Another problem that we have not discussed is that these two inputs are not synchronized well. And because of that, this node is not actually a ground. And because of that, actually there is a capacitor here. It's not ideal. And you know that the capacitor here increases the effect of common mode level, right? You have learned this in analog course. So it's a very important point about that. So now what will happen when the capacitance at this node increases? So eventually you have perturbation at this node, which will have impact on the noise of the current source. Because you assume that this current source is an ideal current source, its value is not changing. But actually what you have in differential mode even is this case, which has the parasitic capacitors as well. And because Vin plus, Vin minus are not perfectly synchronized, so there are actually fluctuations. In fact, usually suppose Vin plus is more than Vin minus, that means left transistor is on. And when left transistor is on, when it turns off, because it's on, it's like a source follower. It still is not turning off completely. If this goes down, this node also will go down. So therefore, it is not really that this node is a clean node. And when this goes down, the current here will change. So eventually, you have fluctuations here. And this actually mainly going down. Because the side which is going up, this transistor still is not on. So therefore, effect will be less. So then, because of that effect, effectively now effect of parasitic capacitors will increase. So therefore, we cannot use a very short, long channel devices here. That is another limitation that we have. And that's why more often this doesn't work well if the value of current is very high or eventually, see, if the resistor is limited to 50 ohm and we want to have a minimum swing, we cannot reduce current below somebody. Suppose if I reduce the current, say for example to even 1 milliampere, I will have only 50 millivolt swing. And for a, say, trace of around, say, maybe 20 inches, these are some of the typical numbers on the PCB for the for those applications, data centers and backplanes. So say suppose you have 25 inches trace. So you have a 50 millivolt. Now you are talking about gigabit, tens of gigabit per second. It has to reach to the other side. And if it is a cable, even if it's worse. So that's why it's not very easy to really reduce the swing. Not to reduce swing then means if we should have enough current. To have enough current, that means aspect ratio should be high. We cannot reduce RO because then we have this problem. Therefore, we cannot really increase L too much because parasitic capacitors will increase. Because we need also a high aspect ratio. So if you put all these points, main thing is because it's high speed. If you just make it low speed, all these issues will go away. It will work much better. In fact, most of the problems come either you want to have significantly high resolution, like 20 bits, at low speed even it's challenging. That's why we have delta sigma ADCs. Otherwise, we will have high speed and then high speed cannot. And here we want to have high speed and high number of bits, that's the problem. If you make it high speed, low number of bits, a few bits, 3, 4 bits is not an issue. If you make it low speed, high number of bits, it still is not an issue. If you make it high speed, high number of bits, it's an issue. Let's put it that way, this RO problem. That's the main thing. So therefore, here now you need RO, for example. Now here say 10 times more, so RO 500 kilo ohm. I consider 10 times. 10 times itself is 10%. That means we have still 10% of the margin for, see, we have half of LSP, 50%. Now we are spending 10% on this. And we have other effects. That's why we prefer really, I mean, we can still spend 10% is okay, but that means that we have now an idea about how to design. Okay, so this was effectively just not to ignore effect of RO. But it doesn't mean you cannot manage it. That's why we have to put them together. These are the things we need. Swing, speed, that means bits per second, or let's say conversion rate, because it's not just bit, because we are giving bits in parallel. So it's a conversion rate actually. Conversion rate, then N, number of bits. R is usually given. If it is not given, then we have a choice. And yeah, usually load is given to us, like the parasitic C. C load. Rest will be parasitic that we create at this node because of these designs. Eventually differential pair design. So these are the most important characteristics. In fact, by having the swing and N, you will get LSP. So you can reduce the current to improve RO for a given N, but swing will reduce, so LSP will reduce. LSP is heavily dependent on IU, of course, we know that, but in voltage domain, it's dependent on IU into R. And IU is dependent on the N. And of course, power consumption actually comes in the second order because this is anyway for high speed. So this is for high speed applications. So I don't talk about power, but there also anyway there is a limit, but for now it's not.